Hi, welcome back. In this video we will discuss multivalent ion batteries. At this moment the rechargeable battery market is dominated by lithium-ion batteries and soon sodium-ion batteries will be widely accessible. Both lithium and sodium ions are monovalent. Their ions have a +1 charge. Multivalent ions are ions that have a greater than 1 charge. When we look at the periodic table and consider the metals, the electronic configuration of the elements dictate the charge of the ions. All alkali metals are charged +1, while all alkaline earth metals are charged +2. For the transition metals it becomes more complex, but most will have a charge of 2+ or greater. Metals like vanadium and chromium can even form differently charged ions. In theory, we could use all these metals to make a battery. And from an academic perspective, this is an interesting endeavor. However, from a practical point of view, it is better to focus on elements that are abundant on Earth. We can also keep the EU critical raw materials list in the back of our mind. Some of the elements that are often looked at are magnesium, aluminum, calcium and zinc. These are all available in great amounts on Earth and their mining and processing is already established. We should keep in mind that there is no multivalent rechargeable battery on the market yet, although there are many people working on pilots at the moment. In this video I want to highlight magnesium and zinc as interesting metals for rechargeable batteries. Magnesium is interesting because in its 2+ charge state it is a similar size as lithium ions. This is very helpful because big ions make it hard to find suitable cathode and anode materials. Magnesium is the 8th most abundant element in the Earth's crust and the 3rd most abundant solute in seawater. It is also involved in many biological processes. And for batteries we are interested in the redox reaction from metallic magnesium to magnesium cations. That is a 2-electron reaction that gives a very decent -2.7 volts. This reaction is more complex to accommodate than a 1-electron reaction. In literature, a common issue for magnesium-ion batteries is the reactivity of magnesium with the electrolyte. Also, it is difficult to form a good solid electrolyte interface with the electrodes. When water is used as an electrolyte, additives need to ensure that water does not react with the magnesium. These are just some of the problems that need to be overcome before magnesium-ion batteries can be commercialized. And personally, I find zinc a very interesting element for a battery. I have a good reason for that, but it is also because Erik and I are working on a new zinc air redox flow battery. We do this in an EU project called Resilient. Zinc is the 22nd most abundant element in the Earth crust and its redox reaction to zinc 2+ gives -0.76 volt. This is much lower than magnesium, but it makes zinc a very good match with an aqueous electrolyte. Zinc is also mined and processed on a very large scale nowadays for other applications. In 2019, it was the 6th most mined ore. In our project, we try to use zinc in a redox-mediated flow battery. When we zoom in on the zinc, we are trying to solve different issues that zinc often has in a battery. Most important being a side reaction where hydrogen is produced and the formation of a thick zinc oxide layer. When we can overcome this issue, we hope we can make a cheap battery for large-scale electricity storage that only contains abundant elements. Zooming out again, there's a whole zoo of examples of multivalent ion battery proposed in the literature. I am sure you will hear about a few being commercialized in a few years. If we can get a few to market, it could really help to diversify the battery market, which would lower prices and increase accessibility.